Right. So at dinner, Val sent a friend to ask me a question, and I said, okay, I'll try and remember, and I'll answer the question at the beginning of my talk. Well, I think your question was, where does all the matter in the universe come from? There's nothing to do with my talk, and so, talk amongst yourselves. At the Big Bang, where does all the stuff come from? Well, the basic idea is at the Big Bang, we have what's called negative gravitational energy. So, if you have two gravitational masses together, you have to put energy in to pull them apart. So that energy that's gone in to pull them apart, we've wound the universe up, so there's lots of negative gravitational potential energy. That balances the positive energy of all the stuff. So the universe started off just as pure energy. As it expanded and cooled, that energy froze out into stuff, into matter and particles. It's all right, fine. All right, there we go. Right, so, but this morning I want to talk about, this is my new passion, the nature of time. What does time mean? And understanding the subject of time is something, it's not like, the Big Bang or black holes or quantum mechanics where we say, all right, Jim, you're the expert, explain. We all sort of have a view on the meaning of time. And what I want to get across is the fact that even in philosophy and physics, there's a whole subject called the philosophy of time, which has been going for a very long time. And we still have mysteries to solve when it comes to what time is. I want to get the time joke out of the way first, which you've probably all heard before. Time flies like an arrow, fruit flies like a banana. There are no funny time jokes. I mean, I know people seem to think on Twitter they can send me time travel jokes and find it amusing. It's not really. Anyway, what I want to then talk about is, there are lots of mysterious aspects to time. So I'll go through a few of them. One of the most basic one is whether time actually exists, or whether it's just an illusion. Is time real? Is it just a way of labeling and ordering events? Is it all subjective? Is it really just the invention of our minds, our brains? And these ideas go back to the ancient Greeks. So Parmenides of Elea, who lived 2,500 years ago, was one of the first people to argue that, in fact, there is no such thing as time. It's all just an illusion. It's all just subjective. Not everyone agreed with him. There's the idea that time exists, it's real, and it flows. The notion of the river of time. And that goes back to another contemporary of Parmenides, Heraclitus of Ephesus, also known as the philosopher of riddles, or Heraclitus the Obscure is one of his nicknames. So that doesn't bode well for someone who's going to explain what time is. But he talks about time as a river. He says time is a real thing. He was obsessed with it. Whereas Parmenides said, no, there's no, surely Parmenides could see that things change, stuff happens, right? Time goes by. But he'd sort of argued himself using logic down a rabbit hole, which he sort of couldn't escape from. The early Greeks had these ideas, and they have developed, but to some extent, a lot of these questions still exist today in modern science. The notion that whether time is made up of snapshots. We perceive time as a continuum. There's no sort of, it's not like watching a film and then saying, yeah, but actually what I'm looking at is individual frames, so many per second. In reality, is time, well, we don't know. It may well be that time is also chopped up down at the tiniest intervals to discrete, static moments. Again, the ancient Greeks has something to say about this. Zeno, who was a student of Parmenides, had all these paradoxes of time. So Zeno's paradox, one of the most famous ones is the paradox of the arrow. If you watch an arrow flying at any given moment, it's static, it's frozen. And so if you put together lots of frozen moments, how do you ever get motion? How do you ever get change? So, but these are still questions we're thinking about today, whether time is continuous, whether it flows. And most interesting for me is the question of whether time has a direction. In a sense, you might think it's sort of tautological to ask, why does yesterday come before today? Well, but that's what the meaning of before means, right? That's the ordering of events. But why does time point in a particular direction? I'll explain why that's actually interesting and why it's profound and has worried physicists for some time now. Partly because of the fact that most of the equations of physics that describe how states of matter change, whether it's Newton's equations of motion, particles moving, whether it's equations of quantum mechanics, they all describe time as going by and systems and objects moving and changing through time. But they're all time symmetric. You can wind it forwards or backwards, and the laws of physics all work. And yet we perceive time to move only in one direction, according to the laws of thermodynamics. And that leads to something called Loschmidt's paradox in the 19th century. How do you reconcile time-symmetric laws of nature with our perception of time being irreversible, not symmetric? Okay, and then finally, there's a question. A lot of cosmologists and people working at the foundations of physics are questioning whether time itself, if it's real, maybe it's not fundamental. Maybe it only emerges as you zoom out, in the same way that temperature isn't a real thing. Temperature is only meaningful when you zoom out and look at trillions and trillions of atoms. You zoom down into the level of atoms and molecules, there's no such thing as temperature, just stuff bouncing around and knocking into each other. So is time also an emergent property? Okay, those are the sorts of questions that are being thought about. We don't know. Let me examine this idea of Heraclitus that time is a river flowing past us from the past to the future. A moment of consideration should convince you that, in fact, that's the other way around. Time flows from the future to the past. It doesn't mean it's going backwards. It just means the future is coming towards us, and then once it's gone past, it's receding past us downstream. That's the past gone behind us. So it's that way around. But is it really that time is flowing past us? Time is one of those subjects, unlike any other aspect certainly within science, where we can detach ourselves and study it and examine it objectively. We are immersed within time. So it's really difficult to extract ourselves and try and argue what time is objectively without interference from our own subjective reasoning. So maybe we are immersed within the river of time. Maybe we are floating through time, observing the world around us, watching it unfold. And in fact, I think that also going back to the ancient Greeks, they said, well, even that picture isn't quite right. You're not facing the future. You're actually facing the past. You're flowing through time, but you're seeing the past receding away from you. The future's behind you. You can't see it. It's coming at you, but you're not looking at it approaching. None of these pictures are really very useful when it comes to rigorous science and the foundations of physics and philosophy, when we're trying to understand where time sits in our understanding of the laws of nature. The notion that time flows, let me just get rid of that idea. There's nothing in the laws of physics that suggests there is a flow to time. And yet we experience time as a flow of moments. Is it really completely subjective? How does that work? Flow of time is regarded in science as an illusion. It's very seductive. Time flows, things change, but it's basically all in our heads. And yet, consider how we appreciate a piece of music. You're not listening to a single note at a time which replaces the previous note. If you listen to any music, there's a continuum, right? You're hearing, more than just that one note or more than just that bar. Without having that continuous experience, we wouldn't enjoy music. What's happening, of course, is that our brain is storing that information from the previous few seconds in the hippocampus, in the brain. That memory is that all those events are ordered, and we perceive them all at once. We only ever experience the present moment. That's the important thing. So the notes that have just gone by, you are not hanging on to when they first came into your ear. That's gone. That's the past. What you're hearing is all these notes at the present moment arranged in a continuous stream. In the same way that when we look at something, I don't just look at a single point in space at any one time. I'm looking at a continuous spread of an image. It enters my eye. My brain's making sense of the world with sounds, appreciating music, and indeed any other thought processes. Things are stored in our memory, and we arrange them in that way. But there's nothing flowing. We only ever experience a single moment of time. When we teach students of physics about the nature of time, it's usually condensed down to Isaac Newton had a picture of time that Einstein showed was wrong. So Newton's idea is our common sense view of time, that there's a cosmic clock ticking by the seconds, minutes, hours, years, independently of our actions within three-dimensional space. Time is absolute and independent. Einstein comes along in 1905 and develops his special theory of relativity and says, no, time and space are not independent of each other. The only way we can make sense of the world is if we combine them together into four-dimensional space-time. Of course, when he goes on then to develop his general theory of relativity 10 years later, where he says, gravity can affect space-time, suddenly this picture of time is that it's real. It has an essence. It's part of the fabric of reality. Four-dimensional space-time is a thing that can be stretched and pulled and twisted and warped due to the action of matter and energy, due to gravity. That's what general relativity is all about. When we say, what's relativity about? it's E equals mc squared. E equals mc squared is the most boring bit of relativity. That's like, so what? Okay, well, if we go on to build atom bombs off the back of it, maybe there's more than a so what about it. But the fact that matter and energy are interchangeable is nowhere near as fascinating as the fact that time and space are combined together. But this change of our view of time from Newtonian absolute time to Einstein's relativistic time still doesn't get to the heart of what the problem is in today's physics. The book that I mentioned in the introduction, The World According to Physics, that I wrote a few years ago, I described the three pillars of physics, of modern physics. And what I want to explain here is how each of them gives us a different picture of what time is. So if we think first of all about what I call the dynamical equations, the equations of physics where time comes in. If you remember school physics, there's a lowercase t. Some quantity changes with time. In physics, we say it's a function of time. It's time dependent. Something that at different times has a different value, like the position of a particle, a ball moving. At a particular time, the ball's over here. At a later time, it's over there. Well, how do you calculate mathematically how that ball is moving? You need to know its speed, its energy, how it's spinning, if it's being acted on by other forces like gravity. All that information gets plugged into a dynamical equation that tells you how the ball moves, how any system evolves. And that's the same in Newtonian physics and the same as it is in quantum mechanics, the theory of the subatomic world. All those equations, any equation that involves stuff that changes with time is called a dynamical equation. And they all have this picture of time as not being a thing. It's not it's not a substance. It's just a number. It's a label. It's called coordinate time. So in this equation that tells you how something changes over time, you say, right, at t equals 10 seconds after I started my stopwatch. You just need to sort of define a particular moment. That's what this thing is doing now. The equation allows you to crank the handle, you solve the equation, to work out what that thing is doing at t equals 20 seconds. But that value of t, that's just a number. It's just a label that tells us what things are doing at that particular value of time. Then you have Einstein's general theory of relativity, where time is not just a label, not just a number, it's a real thing. It's part of the fabric of our four-dimensional reality. Time is now a dimension. It's the fourth dimension. It's an axis. Just like X, Y, and Z directions in space, time is another direction. I can't point to the angle or the direction of the time axis because I need to point out of our three dimensions, and I can't do that. But you can have a picture of, mathematically what it means to have four dimensions, and time is one of those dimensions. Then you have the third pillar, which is thermodynamics. Thermodynamics and statistical mechanics is a subject that describes a lot of how our everyday works in terms of energy and temperature and putting a hot cup of coffee in a freezer. Why does it cool down? Heat transfers from hot to cold objects. That is all part of thermodynamics. And the second law of thermodynamics tells us that always moves in one direction, that time has this arrow, this direction. So in thermodynamics, time is an arrow. That's very different from the other two pillars. We have time as a number, we have time as a dimension, we have time as an arrow. The holy grail of physics is to unify these three pictures, not necessarily three pictures of time, but these three ways of describing our world. We have quantum mechanics to describe the world of the very small, you have relativity theory to describe the very large, and then you have thermodynamics to describe the messy, complicated world in the middle. And we don't know how to unify them together to get a complete picture, what we call a theory of everything. I argue that until we can understand how to reconcile these different pictures of time, we're not going to get very, very far. And there are various problems involved with why time as a number, time as a dimension, time as an arrow is such an issue. In thermodynamics, what was famous, you may have heard of what's called the second law of thermodynamics. Einstein has this famous quote where he says, "Thermodynamics is the only physical theory of universal content which I'm convinced will never be overthrown." Now, here's the guy he came up with general relativity. He's prepared to sacrifice his own theory and admit maybe it's incomplete, maybe there's more to say about it. But thermodynamics, correct. Which is always amusing because this is the second law of thermodynamics. It's so important and yet hasn't even made it to the number one spot on laws of thermodynamics. But thermodynamics says time moves in one direction. The dynamical equations say time can move in both directions. And then general relativity says, well, what does general relativity say? Einstein, when he developed his theories of relativity, it led to this notion that if time is a dimension, an axis, then that means we can picture the entire universe as a static whole, that all times coexist. Now, I can't draw 4 dimensions. I can draw 3 dimensions projected onto 2-dimensional screens, but you can understand, because you're used to looking at solid objects, you know what this 2-dimensional drawing means. It represents something in 3D. But I've had to throw away one of the dimensions of space, right, so that to have my third axis spare to use as the time direction. So space in this case is like this cardboard cutout 2D space. And then the third axis is time. So a slice through that will be what we'd call now. On one side is our past, on the other side is the future. And we, or our consciousness, our perception, is that we are crawling along the time axis. Our now moment is changing. But sitting outside of the universe, viewing God's eye view, if you don't mind me saying, at a humanist convention, would be that all times coexist. That there's nothing special about that slice now, other than the fact that I am experiencing it now. Einstein himself, I think, he famously tried to console the widow of a friend of his at the funeral by, I don't know how much comfort it gave her, but he said the present moment is no more important or less important than all other times. All times are equally important. All times coexist on the time axis. And that's an interesting point, that now time, there's no change in this static picture. This is called the block universe, and all times coexist. The change is our perception of creeping along the axis. A point on that slice, of course, will be where we are in space as well as where we are in time. It's called the here and now. Well, so we have these different pictures of, in relativity, even that notion of a now that we can all agree and accept gets fuzzy, because we have different, depending on our situation, typically if two observers are moving relative to each other at very high speed, they won't agree on when is now. They won't agree on whether two events are happening at the same time, or if event A happens before B or B happens before A. So, when we say now, that's just your now. It may not be somebody else's now. As a famous example, I've taught this for many years to my undergraduates on what's called the relativity of simultaneity. The fact that what one person might regard as simultaneous events will not be seen as such by another observer. And usually the example is you've got two observers flying past each other in rockets. So in rocket A, let's say there are two flashes of light, two events that happen. If the person in rocket A is halfway in between the two and they happen according to that observer at the same time, then he has the right to say they are simultaneous events. But observer B flying past will not see them happening at the same time. Observer B will see one event happening before the other. And neither one of them is correct. They are both correct within their frames of reference. You just have to accept that now and the ordering of events in relativity is relative. Time is relative. The one proviso is you can't have an event happening before another and have another observer saying, no, they happened the other way around, if the first event was the cause of the later event. That then violates what's called causality. You can't have someone shooting a gun and then someone falling, dropping dead, and then someone flying past a rocket, seeing the person falling dead before the gun is fired. Because in principle, they can go and then stop the gun from firing after that person's been shot, which doesn't make any sense at all, particularly on a Sunday morning. And so this idea in relativity, and we have no reason to doubt these notions of relativity for over 100 years now, we've tested them, and it seems that relativity is a thing, and it's correct, suggests that the notion of now loses its meaning. No talk on the nature of time would be complete without some words about possibility of time travel, and I'm doing well because I still have. So we should allow for about 15 minutes, shouldn't we, for questions? Yes, so okay, so 7 or 8 minutes time. Okay, very quick. Time travel. Well, of course, the question of time travel has to be split into two parts. Can we travel into the future, and can we travel into the past? And one's somewhat easier than the other. Traveling into the future, the answer is yes, because we can slow time down. Einstein had two theories of relativity. In his special theory, he said time runs at different rates depending on two observers if they're moving very high speed relative to each other. And so, if you were in a rocket traveling close to the speed of light, below the speed of light, nothing can go faster than light, your time will run at a slower rate as perceived by someone back on Earth. That's called time dilation. In fact, a very simple calculation that I would expect all my physics students to be able to do is this. If you were to travel in a rocket at close, so 0.99999999, I've done the sums, that's how many nines I need, of the speed of light, so almost at light speed, you could cross the entire Milky Way galaxy in a day. Now, this is the thing that makes your head hurt. It still takes light 100,000 years to cross the galaxy. So how can light take 100,000 years and you can only take a day, even though you're traveling slower than light? Well, of course, that crossing it in a day is according to your time, how much time has gone by for you. For someone on Earth, if they could live that long, they would see light taking 100,000 years to cross from one side of the galaxy to the other, and your rocket would take 100,000 plus a bit to get across. So over 100,000 years will have gone by on Earth, but you will have only aged a day. If you then turned around and came back to Earth, you would be in Earth's future. I mean, there'd be no one around that you'd know, apart from that person who seems to have lived for 100,000 years. But you will have traveled into the future. So essentially, we can get to the future by slowing our time down by travelling close to the speed of light. There's another way of slowing time down, and that's due to gravity. Gravity slows time down. This is a famous picture from the film Interstellar. If you haven't seen Interstellar, I recommend it. Brilliant. It's one of my favorite science fiction movies, in part because the nerd in me appreciates that all the physics is correct in Interstellar. It might, if you've seen the film at the end where Matthew McConaughey is floating behind the bookshelf in his daughter's bedroom, all a bit trippy, doesn't violate any laws of physics, though. So. But the fact is, one of the producers on the movie, and indeed the person whose idea it was and wrote the screenplay, is Kip Thorne, Nobel Prize-winning physicist and one of the world experts on Einstein's relativity, Nobel Prize winner. And so here, Matthew McConaughey, they land on this planet that is orbiting a supermassive black hole. And the gravitational field of the black hole is so strong that it literally slows time down. And so they know that for every hour they spend on that planet orbiting the black hole, 7 years are ticking by on Earth because time is running at a different rate. This is not science fiction. The idea is fact. That's what would happen. Gravity really does slow time down. That's how GPS works. GPS wouldn't work if we didn't take into account this idea that time runs at different rates in different gravitational potentials. Satellites in orbit around the Earth, GPS, have to send radio signals to your mobile phone or your car sat-nav to triangulate to work out where you are. Well, they can only do that if they know the exact distance. And you can only know the exact distance if you know speed and time, right? Speed is distance over time. They know the speed because it's radio waves traveling at the speed of light, but they need to synchronize clocks. However, clocks on board the satellite are running slightly faster than clocks on Earth because they're further away from the Earth. So gravity is a bit weaker for them. So it hasn't slowed them down as much as the clocks at sea level, your mobile phone. And so you have to slow down those clocks ever so slightly, tiny fractions of a second, so that they synchronize with clocks on Earth. So time slowing down, that's not very much for Earth's gravity, but find yourself a supermassive black hole, and you can really see slowing time down and therefore a means of getting to the future. Getting to the past, that's a whole nother lecture. I don't have time to go into it. I'll just say, cop out. I'll just say that it's not ruled out by the laws of physics. Einstein's general theory of relativity is our best theory of the nature of time. And it says that in principle it should be allowed. What's ruled out is the paradoxes of time travel. How can you go back into the past and kill your younger self before you've grown up to be a time-traveling murderer? And if you don't grow up to be a time-traveling murderer because you were murdered by your older self, then how did you get murdered in the first place? Right? If you don't get murdered, then you grow up and you do become a murderer, and therefore you don't, and so on. So there are paradoxes of time travel, but we can't rule it out. And there are plenty of science fiction films and stories and TV series and books written about the possibility of creating a time machine, usually involving something called a wormhole, where you can travel back through time, like looping the loop on a roller coaster. You're traveling forward in time yourself, but you're doubling back and arriving where you were before you left. Anyway, that is more on the science fiction side than on the science fact side. I want to, in the last 5 minutes, talk about the notion of the arrow of time, the direction of time. An arrow pointing from the past to the future. So if you look at a film of this jug breaking and smashing into pieces, you can see that film is running in the right direction. It's gone from a very special ordered state of an unbroken jug to one that's broken into lots of different pieces. If we were to run the movie backwards, with all those pieces reconstituting themselves, forming the jug, you'd know this is a film being run backwards. You don't see this happening in the real world. Why is it you only see this thing happening in one direction and not the other? Well, this is what the second law of thermodynamics tells us. It says it's because what's called entropy is increasing. The amount of disorder is increasing. Things unwind, we grow older, batteries run out, balls roll down hills, Children's bedrooms get messier unless intervened from outside. So the jug here is something that has high entropy when it's all broken up, low entropy when it's in the special state where it's reconstituted. The usual example here is with a pack of cards. You start off with a pack of cards that's unshuffled, that's ordered. We say it's in a special ordered low entropy state. But if you shuffle the pack of cards, you're increasing the entropy and you get to the mixed shuffled pack. So the shuffled deck has higher entropy. And shuffling a pack always takes you from the low entropy state to the high entropy state. You don't shuffle a pack and suddenly get one that's fully ordered, unless you're very, very lucky, and that's not going to happen. Don't waste your life trying to do that. So this idea that things move from low to high entropy is what gives us an arrow of time in thermodynamics. The problem, of course, is that, as I mentioned earlier, all our dynamical equations of physics are symmetric in time. They have this property called time reversal invariance. And so this led to what I referred to earlier as Loschmidt's paradox. Time reversal symmetry it conflicts with the idea that we perceive time to run in a particular direction. There are lots of examples of time reversal invariance. So imagine planets orbiting around a star. If I were to run that film backwards, you wouldn't know. You'd say, well, it doesn't violate any laws of physics, the laws of dynamics. They can go around either way. It depends how you set that solar system up in the first place. Likewise, a box of molecules of gas bumping around. If I run that film backwards, you can't tell the difference. They're just bumping into each other, laws of physics, momentum, and so on. And even in particle physics, this is what's called a Feynman diagram, a picture of how you have two particles, A and B. The solid arrows are the path lines, the paths of those particles. The dashed line is some sort of interaction between them, and they create two new particles, C and D. There's nothing in the laws of physics that says you couldn't have particles C and D coming together, interacting and forming particles A and B. So if you zoom down into detail, all our fundamental equations of physics say time is reversible. And yet here's plenty of examples of where time only runs in one direction, not just shuffling packs of cards or dropping china jugs. Ice cubes melting in a warm glass of water. You don't see a room temperature glass of water spontaneously creating a cube of ice floating at its surface while the water warms up. Air leaking out of a punctured tire. You don't see air leaking into a tire, right? Because of the difference in pressure. Radioactive decay. You never see alpha particles finding their way embedding themselves into a uranium nucleus. It's always the other way around. Emission of radiation from hot objects, the slowing down. Friction always slows objects down. Friction doesn't speed objects up, chemical reactions. So all of these are irreversible processes that seem to have emerged from completely symmetric equations of physics. So my last point is that the entropy, this idea of entropy increasing, is in all likelihood, that's the direction that time will go. It's statistical inevitability is a nice way of putting it. Entropy says, or the second law of thermodynamics says, entropy is increasing. Why? Well, it's higher today than it was yesterday. Why? Because it was higher yesterday than it was the day before. So entropy, you can wind it all the way back, and you get to a point where you say, well, that's where entropy was the lowest. The problem is, the equations of physics say if we start with the state of the universe today, tomorrow it'll have higher entropy. But if time is symmetric, then the laws of physics say yesterday, entropy will also be higher. It grows in both directions, forwards into the future and into the past. That's what the equations tell us. How do we get over this idea? Today can't be a special day, that this is the day where entropy is at its lowest and tomorrow will be higher and yesterday will be higher and it gets increasing in both directions. So what's nothing special about today? So let's move the today all the way back to the Big Bang and say that is the special moment when entropy was low. Luckily for us, there's no before the Big Bang. And so there's no worries about where entropy increases before the Big Bang. That's when it starts. That's what's called the initial conditions of the universe. And since then, entropy has been increasing. Why was entropy so low at the Big Bang? Well, we don't know. It's just called the past hypothesis. Cosmologists are really happy with this. Oh, where does the arrow of time come from? Well, second law of thermodynamics and the past hypothesis, which tells you that, that was the condition was special at the Big Bang. But we don't understand why that is. This is work that I'm currently involved in with a philosopher of physics working in San Diego, Eddie Chen. We're trying to get away from this subjective idea of shuffling cards and breaking china jugs and things, and why entropy and second law of thermodynamics. Maybe there's another reason why the universe was special at the Big Bang, and it may have something to do with quantum mechanics, something called quantum entanglement. I'm going to end throwing this idea at you because, again, I'm not going to go into any more detail. It's more just like showing off because we've just had a paper just about to be published on what's called the decoherent arrow of time. I mention it because in all my years of research, never has New Scientist magazine ever taken an interest in my work. But suddenly they picked up on the arrow of time, and it was a news article in New Scientist that the arrow of time comes about, this is our thesis, because the universe started in a very special quantum state. Technically, it's called a pure state. And everything gets entangled with everything else, and the universe moved into a mixed state, and that's why there is an arrow of time. I mention this just to point out that I have no resolution, I have no conclusion to say, well, therefore, this is what time is. Simply the fact that there are still mysteries involved with the nature of time, and there's still mysteries that we're trying to resolve. So I will just end by thanking various people. So Eddie Chen is this brilliant young philosopher in San Diego that I'm working with, and there's several other philosophers and scientists that I've been involved with on this project. Funded by, and again, wonderful for humanists to know that we're funded by the John Templeton Foundation, who, if you know anything about them, they fund research into science and religion. And I'd always shunned, I thought, Templeton Foundation, Templeton Prize. Oh, I'm not quite sure. Yeah, but $1 million, I mean, if they offered it to me. Humanism, atheism, yes, thank you very much. But they said, I said, look, if I apply for the funding and I get this research grant, you're not going to expect my final report to say, and therefore God exists. I said, oh, no, that's, it's fine. So they've been quite hands-off, thankfully, and not questioned whether there's any spiritual, religious aspect to our research. And I will end there. Thank you very much, indeed.
Lovely. Have a seat.
Thank you.
So thank you, Jim. That was brilliant. So inspired example, such lovely use of music.